Alright, let's start off by looking at some examples of the mirror equation in action. So we're going to go through a couple of examples here. So I have a convex mirror with a focal length of 10 centimeters, and it produces an image of an object which is located 20 centimeters from the mirror. So we're told that the image is we're told that the object is located 27 meters from the mirror. It's not very clear in that question. So we want to determine the image distance and the magnification. Is the image real or is it virtual? We have a lot going on here. A good idea, write a variable list for what's going on here. So as I mentioned in the last video, when we have convex mirrors, they're trying to trap you. Convex mirrors, the focal length has to be input as a negative. So instead of saying the focal length is 10 centimeters, when we're doing the calculation, we're going to put it in as a negative 10 centimeters. Now someone might ask, well, why are we saying focal length 10 centimeters and not negative 10? When we're talking about focal lengths, we do quote it as a positive value. So saying it's 10 centimeters is appropriate. When we're using it mathematically, however, that's where we have to put in that negative. And then we're told that DO is just 20 centimeters. Again, DO is always going to be positive because you're always going to have real objects. So I have F, DO, I'm interested in DI, and I'm also interested in the magnification. Well, I know the relationship between F, DO, and DI. That is going to be from our lovely mirror equation here. Now, I would like to find DI. With the mirror equation, before we find DI, let's just find 1 over DI. So we need to get rid of this 1 over DO on both sides. So what's going to happen here is I'm going to be left with 1 over F minus 1 over DO. This is going to be equal to 1 over DI. This allows me to actually calculate the inverse of the distance, so I can put that in. So I know my focal length is negative 10 centimeters. That negative is really important. And then I'm going to subtract from that this inverse of the object's distance. So again, we're going to be really careful when we put this in, being mindful of that inverse, being mindful of this negative here. So when I calculate this, I'm going to get negative 0.15 centimeters. And it's going to be centimeters inverse, just because you'll notice the units of centimeters are on the bottom here. They're in the denominator. And we also want to recall, just kind of like from math, so like centimeters to the inverse is like the same thing as 1 over centimeters. So we just have to watch for that. So I'm getting that 1 over the distance of the image is negative 0.15 inverse centimeters. Big mistake that students make here is they say, oh, there's my DI. No, you found 1 over DI. So to find DI, we just have to invert this, or we just got to flip it, or do 1 over. So DI is going to be 1 over this number. So if we do the inverse of that, we're going to get about negative 6.67 centimeters. Because now 1 over centimeters is just going to give us centimeters. So the units are a little bit finicky on this, just because, again, we're dealing with fractions and all that. So I get DI is equal to negative 6.67 centimeters. So then we also want to find the magnification. So for the magnification, we know that we have HI over HO, and this is negative DI over DO. We use whichever one is most helpful to us. I don't know anything about HI, nor do I know anything about HO. So we're not going to use that. We're just going to say the magnification is negative DI over DO. So we just found the image distance is that negative 6.67, so make sure that that goes in there. Like that negative in front and that negative is really important. And then we're going to divide that by DO, which is just 20 centimeters. So what we're going to get is we're going to get about a positive 0.333. Now you may see people put like the little X here, like for times. You don't put that, not a big deal. But just basically what this is trying to tell you, a magnification of 0.333. The image is 0.333 times the size of the object. So it's about a third smaller. Now it's asked us, is the image real or virtual? If you want to know if the image is real or virtual, you check the sign of DI. So we're going to check the sign of DI. Not DO, not HOM, any of that. We're checking the sign of DI. If DI is a positive, that is for a real image. If DI is negative, it's going to be a virtual image. Because DI is negative, that's telling us it's on the other side of the mirror relative to the object. This is going to be a virtual image. So it's a virtual image just because that image distance is negative. And a lot of times what students get trapped on is they start to look at object heights and they'll be like, oh, the image heights, and they'll be like, oh, the image height's negative. It's a virtual image. Nope, you can absolutely have, and in fact, if your image height is negative, you most likely do have a real image. In fact, that's always going to be the case because a convex mirror always produces an upright image. So if you have an inverted image, then you know it's going to be real. So we have to be really careful with that. Now, the next example here, this is meant to be more a little more abstract because this time we're not giving you a lot of concrete numbers to work with. So we're going to have an object. It's going to be placed some unknown distance in front of a concave mirror. And we're told that its real image, it's located about 3x centimeters in front of the mirror. We're told the focal length is about 2.5 centimeters. So we want to determine the object and the image distances from the mirror. So we'd like to find DO and DI, like actual values. So in this question, we have been told that DO is some x value that we don't know about. We also are told the real image forms at this 3x. And we know the focal length is 2.5 centimeters. So it doesn't look like we have a lot to work with, but we can still go ahead because we know that 1 over the focal length is 1 over DO plus 1 over DI. Now, we can start to sub some things in. So we know the focal length here is 2.5 centimeters. We know DO is x. We don't know anything about it. X centimeters. And we know DI is 3x centimeters. Now, we might say this looks ugly. It does, but we're going to do a little bit of work on this because we can certainly iron out some of the wrinkles on this. Now, what we're going to do here is we're going to work with the right side. If we can get like one fraction equals just a single fraction, that will make our life easier. What we'd like to do is we'd like to combine this here. Well, I can't combine denominators when they're not the same. Like x and 3x aren't the same. But we can make a common denominator out of these. Because the way to make x into a 3x, well, we just have to put a 3 in front. But remember, what we do to the top, we have to do to the bottom. So instead of saying 1 over x, we can say this is 3 over 3x. What this allows us to do is this allows us to simplify the right side here. So we have a common denominator of 3x, and then 3 plus 1, that's going to give me 4. So now I have fraction equals a fraction. So I'm going to do something that your math teachers, they will hate me for. They do not like us doing this in physics, but I'm going to do it anyways. We can cross multiply. So I can multiply the 1 and the 3x. I can multiply the 4 and the 2.5 centimeters. So what I'm going to get here is 3x times 1 is 3x. 4 times 2.5 centimeters is 10 centimeters. So at this point, we can solve for x. Now, I'm just going to stop it here. We want DI. We know that DI is equal to 3x. Well, we know 3x is 10 centimeters, so we might as well just mark that down now, just to save us the trouble. And then we want to find DO, which is just going to be x, so we're going to divide both sides by 3. So we're going to get x equals 3.3 centimeters. So I can kind of mark that on my side up here. So to finish up this question, we could just say, okay, based on everything that we got, we know that DO is 3.3 centimeters, and then based on the type of mirror that we have, this is going to form an image that is located at 10 centimeters away from the mirror on the same side of the mirror, since it is a real image. And that's just to kind of show you how we deal with this when we don't have actual concrete numbers to work with. This is a pretty common thing on an exam too, so watch for these.